What if a single particle held the secret to everything? The reason the universe has mass, the key to why anything exists at all. For decades, scientists hunted for this elusive element of reality, a subatomic ghost so vital that without it, the cosmos would be a lifeless void. Some called it the Higgs boson. Others more dramatically called it the God particle. But what is it really? And why does it matter? To answer that, we have to go back, not just to the birth of the particle itself, but to the moment time began. Picture the universe in its first trillionth of a second. There's no matter, no galaxies, no atoms, just a quantum soup of energy, seething with potential. The forces we now know, gravity, electromagnetism, and the strong and weak nuclear forces, are not yet distinct. Everything is unified in a high-energy symmetry, but something breaks that symmetry. Something triggers the creation of mass, and that something is the Higgs field. Imagine the Higgs field as an invisible ocean that fills all of space. As particles move through it, some interact with the field and are slowed down. This resistance is what we call mass. Without it, particles would zip through the universe at the speed of light, unable to form atoms, stars, or us. The Higgs boson is the quantum fingerprint of that field, the smallest detectable ripple in this all-pervading medium. For decades, the Higgs boson remained a theoretical prediction. Proposed in the 1960s by Peter Higgs and others, it was a cornerstone of the standard model of particle physics. But there was no proof. No one had ever seen it. Detecting the Higgs boson would require smashing particles together at unimaginable energies to briefly recreate the conditions of the early universe. That's where the Large Hadron Collider comes in. Buried beneath the Franco-Swiss border, the LHC is a 27-kilometer ring of superconducting magnets and detectors, capable of accelerating protons to 99.9999991% the speed of light. When two of these protons collide, the energy of the crash converts into mass, thanks to Einstein's EXMC2, allowing rare particles to pop into existence for the tiniest fractions of a second. Among those scientists hoped would be the Higgs boson, and on July 4, 2012, the world got its answer. Scientists at CERN announced the discovery of a new particle with a mass around 125 giga-electron volts. Its behavior matched predictions. It decayed into the right combinations of other particles. It was the long-sought Higgs boson. The God particle had been found. But the name God particle is misleading. It was coined not by scientists, but by Nobel laureate Leon Lederman, originally as a marketing hook. In fact, Lederman had wanted to call it the goddamn particle because it was so frustratingly hard to find. But his publisher disagreed. Still, the name stuck. And while it's not divine, the Higgs boson does play a godlike role. It makes the universe possible. Without the Higgs field, all particles would be massless. Electrons wouldn't bind to nuclei. Atoms wouldn't form. Chemistry wouldn't exist. There would be no matter, no stars, no life. The Higgs boson is not just another particle. It's a key to the very fabric of existence. But here's where things get even more interesting. The discovery of the Higgs boson was supposed to complete the standard model, the elegant framework that describes all known particles and forces. And in a sense, it did. The puzzle was complete. The theory matched the data. But in doing so, it also raised new, unsettling questions. First, the mass of the Higgs boson itself is problematic. The equations of quantum field theory suggest that its mass should be far, far higher, closer to the Planck scale, where gravity becomes as strong as other forces. But the Higgs mass is relatively low. This discrepancy is called the hierarchy problem, and it suggests there's something missing, some mechanism that keeps the Higgs mass in check. Supersymmetry, extra dimensions, nobody knows. Second, the Higgs field might not be stable. Calculations based on its mass and the mass of the top quark suggest that we live in a metastable universe. That means the Higgs field is in a false vacuum, a temporary state that could, in theory, collapse. If that happened, it would trigger a vacuum decay, a bubble of true vacuum expanding at the speed of light, destroying everything in its path. It's not likely to happen anytime soon, but it could. The God particle might one day end the universe as we know it. Third, the Higgs discovery deepens the mystery of the Big Bang. If the Higgs field is responsible for mass, what created the Higgs field? Why does it exist at all? Why does it have the strength it does? These are not just questions of physics, they are questions of origin, of causality, of why there is something rather than nothing. And this brings us to a bold, speculative idea. Some physicists believe that the properties of the Higgs field may hold clues to the multiverse. According to the theory of cosmic inflation, our universe is just one bubble in a vast foam of universes. In each bubble, the laws of physics may be different. Different particles, different forces, different values for the Higgs field. Most of these universes would be barren, lifeless, but a few, like ours, would support complex structures because the Higgs field happens to have just the right value. If that's true, then the Higgs boson is not just the fingerprint of a universal field. It's a ticket to the multiverse, a hint that our universe is just one of many, selected not by design, but by chance. We live here not because it was meant to be, but because it works. The God particle in that sense is not proof of intention, but of cosmic lottery. Still, the Higgs boson remains one of the most profound discoveries in science. It confirms that mass is not an intrinsic property, it's an interaction. That what we call substance is the result of particles wading through an invisible field that pervades everything. The chair you sit on, the screen you're watching, your own body. All of it owes its mass to a field that was once just an idea and is now a measurable reality. But we're just beginning to understand its implications. What if the Higgs boson decays in unexpected ways? What if it connects to dark matter or reveals new forces? What if it's not the only Higgs? The Standard Model has given us the blueprint, but the universe, it seems, still hides deeper secrets. The discovery of the Higgs boson was a triumph, but it also opened a doorway into a darker, stranger frontier, one where the known laws of physics begin to fracture. To understand just how deep the mystery goes, we need to confront the limits of the Standard Model itself. The Standard Model is arguably the most successful scientific theory in history. It explains the behavior of all known particles and their interactions, with the exception of gravity. It describes 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. It predicted the existence of particles long before they were discovered, like the W and Z bosons, the gluon, the top quark, and finally, the Higgs boson. Its equations are astonishingly accurate, and yet everyone agrees it's incomplete. One of the most glaring problems is dark matter. Observations of galaxies show that there's far more mass present than we can see. Stars at the edges of galaxies orbit too quickly to be held by visible matter alone. Gravitational lensing, the warping of space around massive objects, shows more gravity than we can account for. Physicists estimate that about 85% of the matter in the universe is invisible. It doesn't emit light, it doesn't interact with the electromagnetic force, and it doesn't fit into the Standard Model. The Higgs boson, for all its significance, doesn't explain this missing mass. Then there's dark energy. In the late 1990s, astronomers discovered that the expansion of the universe isn't slowing down, it's speeding up. Something is pushing space apart at an accelerating rate. This force, dubbed dark energy, makes up nearly 70% of the universe. Combined with dark matter, that means the Standard Model describes only about 5% of what actually exists. It's like having a map of a city that only shows a single street. We're missing almost everything. The Higgs boson's discovery didn't solve these mysteries, it deepened them. Its existence confirms that fields can permeate space and shape the universe. But if the Higgs field exists, why not others? Could there be a dark Higgs field that gives mass to dark matter particles? Some theories propose this exact idea. a hidden sector with its own particles, forces and fields, interacting with our universe only through gravity or rare quantum effects. This leads to the concept of portals, mechanisms by which our visible universe and a dark sector could occasionally interact. One such idea is the Higgs portal, the possibility that the Higgs boson could decay into dark matter particles. If we could observe such a decay in the LHC, it would be a revolutionary breakthrough. But so far, no definitive evidence has emerged. The search continues. There's also the issue of unification. In the early universe, the forces of nature were united. As the universe cooled, they separated into the distinct forces we observe today. The electroweak force, now split into the electromagnetic and weak nuclear forces, was unified until a fraction of a second after the Big Bang. The Higgs field was responsible for breaking that symmetry. But what about the strong force? And gravity? Physicists dream of a grand unified theory, one that unites the strong, weak and electromagnetic forces into a single framework. Even more ambitious is the theory of everything, which would include gravity as well. The Higgs boson is a piece of this puzzle. Its properties, interactions and quantum behavior are crucial data points. Some extensions of the standard model, like supersymmetry, predict a whole zoo of new particles, including partners for the Higgs itself. These theories attempt to solve the hierarchy problem and provide candidates for dark matter. But so far, experiments haven't confirmed any of them. And then there's gravity. The standard model doesn't include it because gravity is described by an entirely different framework: general relativity. While quantum field theory explains the microscopic world with astounding precision, general relativity governs the large-scale structure of space-time. These two theories work perfectly in their own domains, but they're fundamentally incompatible. The clash becomes most severe at the Planck scale, an unimaginably small distance where quantum effects of gravity become significant. To unite quantum mechanics and gravity, physicists are developing quantum gravity theories like string theory and loop quantum gravity. In these models, particles are not point-like, but tiny vibrating strings or quantum loops of space-time. The Higgs boson in these frameworks is just one vibration mode among many. But string theory is hard to test. It operates at energies far beyond our current reach. We need a new kind of physics to bridge the gap, and the Higgs might be our best clue. The Higgs boson is also tied to the concept of vacuum energy, the idea that empty space is not truly empty, but filled with quantum fluctuations. The energy of the Higgs field contributes to this vacuum energy. But when physicists calculate the expected vacuum energy from quantum fields, the result is staggeringly wrong. The predicted value is 120 times larger than what we observe. This discrepancy, known as the cosmological constant problem, is the worst prediction in the history of science. It suggests that something fundamental is missing from our understanding. Some believe that the solution lies in the multiverse. If there are countless universes, each with different values for fundamental constants, then we just happen to live in one where the Higgs field, and thus the vacuum energy, takes a value compatible with life. This is the anthropic principle, the idea that we observe the universe as it is because only certain conditions allow observers like us to exist. It's controversial. Some see it as a cop-out, a philosophical dead end. Others view it as a profound insight into the nature of reality. At the same time, new technologies are allowing us to study the Higgs boson in greater detail. Future colliders, like the proposed Future Circular Collider or the International Linear Collider, aim to produce millions of Higgs particles, allowing precise measurements of their properties. Any deviation from the standard model predictions could hint at new physics. The Higgs boson could be a doorway to extra dimensions, to hidden symmetries, or to entirely new realms of matter and energy. But the implications of the Higgs boson aren't limited to physics alone. They touch on some of the oldest questions humanity has ever asked. Why is there something instead of nothing? What is the origin of form and structure? Is the universe the product of chance, necessity, or design? In religious and philosophical circles, the term God particles sparked intense debate. Some saw it as evidence of a divine order. Others criticized the name as misleading or sensationalist. But whatever you call it, the Higgs boson is a symbol. It represents the edge of our knowledge, the place where human curiosity meets the unknown. It reminds us that the universe is not static or fully understood. It is dynamic, mysterious, and still full of secrets waiting to be uncovered. And perhaps that's the true power of the Higgs boson. Not just that it gives mass to particles, but that it gives momentum to our quest for meaning. It stands at the boundary between what we know and what we can still discover. A particle born in the fires of the Big Bang, still whispering to us across billions of years, "Keep going, you're not done yet." If the Higgs boson is the key to understanding why particles have mass, then it also holds clues to something even deeper: how the universe itself came into being. To grasp this, we need to go back to the very beginning, to a moment before time as we know it existed, to the Big Bang. According to the standard cosmological model, the universe began about 13.8 billion years ago in an unimaginably hot, dense state. In the first trillionths of a second, all the fundamental forces were unified. There was no light, no atoms, no space as we experience it, just pure seething energy. Then, in a rapid burst of expansion called inflation, the universe grew exponentially, smoothing out any irregularities. As it expanded and cooled, the fundamental forces separated, particles formed, and the first elements were born. But here's the mystery. During those first microseconds, all particles should have been massless. According to the equations of the Standard Model, mass only emerges when the Higgs field switches on. Before that, there was no distinction between massless and massive particles, just pure kinetic chaos. It was only when the Higgs field acquired a non-zero value across the universe, a process known as spontaneous symmetry breaking, that particles like electrons, quarks, and W and Z bosons acquired mass. This moment, when the Higgs field crystallized into place, is one of the most critical events in the history of the cosmos. Without it, atoms couldn't exist, matter wouldn't clump. Stars, planets, and life would be impossible. It's not an exaggeration to say that the Higgs field shaped the universe into a place where complexity could emerge. But why did the Higgs field take the value it did? Why didn't it remain at zero, leaving the universe filled with massless radiation? Or collapse into a different configuration where physics works differently? These aren't just questions of curiosity, they're fundamental to our existence. And right now, physics doesn't have a solid answer. The potential energy of the Higgs field is described by something called a Mexican hat potential, a three-dimensional curve that looks like a sombrero. At the top of the hat, the field has zero value, and the universe is perfectly symmetric. But that point is unstable. Like a marble balanced at the top of a hill, the field eventually rolls down into the valley of the hat, where the symmetry is broken and particles gain mass. The exact shape of this potential determines how the Higgs field behaves and why it took on the value that it did. Now here's where things get truly strange. According to some theories, the Higgs field may not be in the true lowest energy state, but in a false vacuum. This is a metastable state, stable for now, but not forever. If that's the case, then the universe is living on borrowed time. At any moment, a quantum fluctuation could cause a region of space to tunnel into a lower energy true vacuum. This would create a bubble of new physics that expands at the speed of light, annihilating everything in its path. No warning, no escape. The laws of nature would change instantly, and the universe as we know it would cease to exist. This is known as vacuum decay. It sounds like science fiction, but it's grounded in real calculations. Based on current measurements of the Higgs boson's mass, about 125 GeV, and the top quark's mass, the vacuum appears to be metastable. It's not guaranteed, but it's possible. The only reason it hasn't happened yet is that the timescales involved are vast, trillions upon trillions of years. Still, the fact that our universe might be perched on the edge of a quantum abyss is profoundly unsettling. But it also opens another line of speculation. What if this isn't the first universe? What if the Higgs field in other regions of a larger multiverse settled into different values? In some bubbles, maybe symmetry was never broken. In others, the field took on extreme values, creating universes with no chemistry, no galaxies, or dimensions that curled in on themselves. Ours is just one valley among countless possibilities, and we live here because it's one of the few where life is possible. This idea isn't just poetic. It has scientific implications. If we could find evidence of Higgs field variations in space, maybe through subtle anomalies in the cosmic microwave background, it could support the multiverse hypothesis. Alternatively, we might discover other scalar fields with similar properties, hinting at a larger framework beyond the Higgs. Some physicists propose that the Higgs is just one member of a broader family of fields, each with its own role in shaping the universe. In this view, mass is just one expression of a deeper, hidden architecture of reality. These ideas are speculative, but they are driving some of the most ambitious theories in physics today. There's also the mystery of why the Higgs boson is so light. According to quantum field theory, it should receive massive corrections from interactions with other particles, pushing its mass toward the Planck scale, 10^19 GeV. But it doesn't. Somehow its mass is protected, staying around 125 GeV. This is called the hierarchy problem. Supersymmetry, extra dimensions, and other theories have been proposed to explain this. But so far, the LHC hasn't found evidence for them. The question remains, why is the Higgs boson so delicately balanced? Is there a hidden mechanism we haven't discovered yet? Or is it pure chance? A cosmic accident in a multiverse of possibilities? Even the nature of the Higgs boson itself is unclear. Is it a fundamental particle, or is it composed of something deeper? Some models suggest that the Higgs is a composite particle, made of more fundamental constituents bound together by unknown forces. This could help solve the hierarchy problem and suggest a richer underlying structure to reality. All of this leads to a sobering conclusion. The Higgs boson is not the end of the story. It's the beginning of a new chapter, one that forces us to rethink the nature of mass, the origin of the universe, and the stability of everything we hold dear. In that sense, calling it the God particle is more than just a dramatic nickname. It's a recognition that this tiny quantum excitation, barely existing for a fraction of a second in the heart of a collider, has implications that reach across the cosmos. From the structure of galaxies to the beating of your heart, from the formation of atoms to the question of why anything exists at all, the Higgs boson casts a long, invisible shadow. It's not just about physics. It's about meaning, about origins, about fate. And as we continue to explore its secrets, one thing becomes clear. The God particle may not answer every question, but it ensures we'll never stop asking. So what have we learned from the Higgs boson, the so-called God particle? That the universe is far stranger, more delicate, and more precariously balanced than we ever imagined. That mass, existence, and reality itself hinge on a quantum field invisible to our senses, yet omnipresent. That beneath the apparent simplicity of matter lies a puzzle still unsolved, a riddle woven into the very structure of space and time. We once thought finding the Higgs would close the book. Instead, it opened 1,000 new pages. And maybe that's the true legacy of the God particle. Not answers, but deeper, better questions. Because sometimes the more we discover, the more mysterious everything becomes.